In this lecture, we're going to start integration. We're going to have multiple types of integration over different domains. Today, we're going to look at double integration over rectangular domains from the xy plane. So capital R here denotes a rectangle in xy space. So here, AB cross CD means that x comes from the interval a to b, so it's like a is less than or equal to x is less than or equal to b, and y comes from the closed interval from c to d. So that's what I've tried to sketch over here in the xy plane. This is the rectangle R. We're going to first start by assuming that we have a continuous function over R. So I can superimpose R in R3 by imagining that this rectangle is down here. Try to rotate my R so that you can see how that works. So our rectangle goes from A to B on the x-axis and from C to D on the y-axis. And then when we get over to it in this third picture, there's R again. Now suppose this wavy piece of paper I've sketched up here is the graph of our continuous function z equals f of x and y. In other words, every point on this graph has the form x, y, f of x and y, so that's the z coordinate. Now the way I've sketched this, the graph of our function sits up over the rectangle and is enclosing a solid region between the xy plane and the graph of the function. So every point in S has the form x, y, z, where x and y belong to R, and z is between the xy plane and the graph of the function. Here the function is positive, but it is possible to consider functions which have negative outputs, in which case you would just be looking at z coordinates between the graph of the function and the xy plane. When we compute the double integral of this function over this rectangle, what we're going to be doing is computing the volume of this solid S enclosed between the xy plane and the graph of our function. So the goal with today's lesson is to set up the Riemann sum that we would use to compute this volume, or to estimate it first, and then we'll compute the actual volume by taking a limit. So in this video, we're going to focus on the definition of integration, but then later we'll have faster techniques so that we can integrate in practice a lot more quickly than we will in this particular lecture. When you studied integration in single variable calculus, what you did was you took your domain, a closed bounded interval from A to B, and you chopped it up into little pieces. That's what we're going to do here to our domain R, this rectangle in the xy plane. What we're going to do is we're going to chop perpendicular to the x-axis, that's going to slice up the x-coordinate, and perpendicular to the y-axis, that's going to slice up the y-coordinate. And after I've done that partitioning process, what we create here is a bunch of subrectangles. We want to index through these subrectangles, so what we say is that the lowest x-coordinate A will have subscript 0, so that's the x sub 0 coordinate, and then x1, x2, x3. If you've defined n intervals along the x-axis, the final coordinate is x sub n, and that corresponds to b, the upper bound for the x variable. Similarly for y, the starting value for y will index as y sub 0, and then we'll have y1, y2, y3, y4, all the way through the final slice for y, which will be y sub m. M may be the same as n, but it doesn't have to be. So we could have n subintervals along the x-axis and m subintervals along the y-axis, defining this family of m times n total subrectangles. Okay, let me look at one particular subrectangle. Typically, when we index through our x values, we'll use the letter I, and when we index through the y values, we'll use the letter j. So let's imagine that after doing these chops, I come to a random subinterval on the x-axis. Let's call this the ith subinterval, and since we started counting x values from 0, it needs to start from x sub I minus 1 and go through x sub I. Similarly, if I come to the jth subinterval along the j-axis, that's going to go from y sub j minus 1 through y sub j. These values of x and y enclose one particular subrectangle. Let's say it's this one right here, and let's kind of zoom in on it. Okay, so there's one particular subrectangle from my domain. This subrectangle can be thought of as xi minus 1 through xi cross yj minus 1 through yj. So that's the rectangular notation for this subrectangle. So I for x, j for y. If this side is parallel to the x-axis, then the length of that side will denote as delta xi. And similarly for the other side, its length is delta yj. And how you compute those side lengths is you just do right point minus left point. So delta xi is xi minus xi minus 1. It's the length of that little subinterval from the x-axis. And similarly, delta yj is yj minus y sub j minus 1. These are side lengths on a rectangle. So you multiply them together and you get an area. This will be the area of that subrectangle. So what we'll denote as delta A sub ij is the area of the ijth subrectangle. Now what we're going to do is come to our ijth subrectangle and choose a special point. I like to think of it as the representative point for that subrectangle, which we denote as xi star, comma yj star. So that's a choice of point from this subrectangle. It could be one of the vertices, or it could be this point kind of randomly in the middle like I've sketched. We take that point and we plug it into our function. That gives us the z-coordinate of this point up here, which gives us a height to associate to a rectangular prism that we could draw over this subrectangle. I want to emphasize here that f is scalar valued, so I'm pointing at a point which has an x, y, and z coordinate, but f of xi star, yj star is the z value of that coordinate, so that's the height of this point over the xy plane. Okay, now if we did this for every subrectangle, we would have a family of rectangular prisms approximating the volume enclosed between the xy plane and the graph of this function. But for every subrectangle, you would choose that representative point, compute the associated height, and then we would have that the volume of that solid S is approximately the sum of a bunch of rectangular prisms, like rectangular cubes. Now, how do you compute those rectangular volumes? Well, it's just height, which is f of xi star yj star for each subrectangle, times the base, which is delta aij. So just height times base, approximating the volume enclosed between the graph of the function and the xy plane. In a minute, we will set up and solve a Riemann sum in order to compute the volume enclosed between the graph of a function and the xy plane for an actual function over a given rectangle. But before we do that example, let's just step back and talk through the process. In my picture, I tried hard to make sure that the intervals along the x-axis and the intervals along the y-axis were not all a consistent length. Because when we do Riemann integration, we don't actually require our subintervals or our subrectangles to all be the same size. But in practice, if you're actually going to compute an integral using the definition, it's much easier if you do have a consistent size. So when we do an example of this in a second, we're going to set up our subrectangles so that they are all the exact same dimensions. And that is a choice we make for convenience. Then the first thing we're going to do is compute delta x and delta y. Since the subrectangles are all the same size, we're not going to have delta xi and delta yj depending on the subrectangle I and j. If our subrectangles are not evenly sized, then delta x and delta y may depend on the subrectangle, but in this case they won't. So with that observation, for me the first step is to compute delta x and delta y. To compute delta x, if we have n subintervals along the x-axis, we need to divide the interval from a to b up into n even pieces. The width of each piece would be b minus a divided by n. Similarly, delta y would be d minus c divided by m. We can also chop up our domain so that m equals n. So that choice is not required, it's something that we may do for computational convenience. The next thing we're going to do is identify a consistent choice of point xi star, yj star for each subrectangle. Again, the consistency is not required, but by saying for every single subrectangle, I'm going to pick the lower left corner, we can do our computation a lot more efficiently. Then we set up and evaluate our Riemann sum. This is going to be a double sum because our domain is two-dimensional. We need to add up over the x-coordinates, that's summing with respect to I, and add up over the y-coordinates, that's summing with respect to j. So what this double sum does is it first fixes I equal to 1. That puts us in this first strip perpendicular to the x-axis. Then it says do some computation down the y-axis. So this double sum means first fix an x-interval and sum up over all the y-intervals. Then I equals 2. So we go to the second subinterval for x and then add up across the y-coordinates. All the way through, when I equals n, we're here, and then we sum up across y. So that's how the double sum works. What are we adding up? Well, a bunch of prism volumes, which is going to look like special height times area of the base. Since we're assuming that we're working with evenly sized subrectangles, I can simplify the delta x, delta y a bit by plugging in what we computed in step 1. So here I'm just replacing delta x and delta y with b minus a over n and d minus c over m. b minus a over n and d minus c over m are just numbers. A, B, C, D, N, and M are all fixed numbers. They don't depend on I and j, so we can factor that product out in front of the double sum. That ability to pull delta x and delta y out in front of the double sum is only permissible because we have evenly sized subrectangles. So if delta x and delta y had depended on the index I and j, if we had delta xi and delta yj, then we wouldn't be able to do that. So this is one reason why we've chosen to simplify our lives this way. Okay, I think I can fit step 4 on here. That's just to take the limit of the sum as n and m go to infinity. If the limit of the Riemann sum exists, then our function is integrable, and that limit is the volume enclosed between the graph of the function and the xy plane. Okay, let's work through this process now for a specific function. It's going to be a fairly easy function because this is a hard calculation to do. Or it's not always difficult, but in my opinion, it can be tedious. So we are going to compute the double integral of x plus y dA over r. So in this notation, x plus y is the function. We can write f of x and y equals x plus y. dA is our general differential here to indicate that we're integrating over a region that has area. And in particular, the domain that we're integrating over is the rectangle from 0 to 1 for the x-coordinate and 1 to 3 for the y-coordinate. As we just talked through, we're going to use evenly sized subrectangles to simplify our lives, and then we'll also make the choice of upper right endpoint for our special representative point for each subrectangle. Let's also choose to cut up the domain in such a way that we make the same number of slices perpendicular to the x and y axes. So in other words, we're going to have n and m be the same. Okay, step 1 was to find delta x, delta y, and then we can go ahead and multiply them together to say what the area of each base is. So the width of every single subrectangle with respect to x is delta x equals b minus a divided by n. So for this domain, that's going to be 1 minus 0 divided by n. Similarly, delta y is going to be d minus c divided by n. So for this domain, that's 3 minus 1 divided by n. So the area of the base for each subrectangle is delta A, which is the product of delta x and delta y. So for this problem, that's going to be 2 over n squared. Per our simplification on the previous slide, that's a term that we're actually going to be able to put out front in front of the double integral when we move on to step 3. In step 2, we're instructed to choose the point for each subrectangle to be the upper right endpoint. So let me sketch a few. Okay, so say that this is 4 subrectangles, and actually let me label the points forming them as the first 3 points for x and the first 3 points for y. For our first subrectangle, the 0, 0th subrectangle, we're going to choose the upper right point. And then for this subrectangle, that's the 1, 2 subrectangle, we're going to choose this point. For the 2, 1 subrectangle, this one, we'll choose this point. And for the 2, 2 subrectangle, we'll choose this point. We need to be able to describe xi star, yj star in terms of I and j, because we're going to index over I and j. So for the 1, 1 rectangle, I equals 1, j equals 1, notice the point was x1, y1. Let's see if that holds in general. So if I come up to the 1, 2 subrectangle, the upper right corner is x1, y2. If I come to the 2, 1 subrectangle, the upper right corner is x2, y1. And in the 2, 2 subrectangle, the upper right corner is 2, 2. So that works out. Okay, so now we have a convenient way of identifying the representative point for each subrectangle. We're going to have to plug that point into F. So let's see if we can find any more information about xi, yj. So what do the points xi look like? Well, the first one is x0. That's just the first x coordinate, 0. x1 is 0 plus 1 over n because I take a step of delta x down the x-axis. x2 is x1 plus 1 over n, but that's actually going to be 0 plus 2 over n. So let me just write 2 over n. You can check x3 would be 3 over n. And the pattern holds because our final point would be x sub n is n over n, and indeed that is 1. That's the right point for x. What do the yj's look like? The first one, y sub 0, is 1. The first step we take, we arrive at the point y sub 1, and that step size is 2 over n, so that's 1 plus 2 over n. Then the second step would arrive at 1 plus 2 over n plus 2 over n, so 1 plus 4 over n. Y sub 3 would be 1 plus 4 over n plus another step, so 1 plus 4 over n plus 2 over n means we arrive at y3 equals 1 plus 6 over n. So the jth one would be 1 plus 2j over n. And let's see if the last one matches up. 1 plus 2n over n is 1 plus 2, which is 3, which is indeed the highest point for y. Okay, this means that we can say a little bit more about xi star, yj star. It's xi, yj, but now we have more specific coordinates for those. So our conclusion is that xi star, yj star, we first simplified to xi, yj, and we're simplifying it further now to I over n, that was the pattern for the xi's, 1 plus 2j over n for the yj's. So those are the points that we're going to plug into the function in order to compute the heights of the prisms that we use to estimate the volume. Okay, now we're going to set up and solve the Riemann sum. I have some summation identities at the top, but let's come to those when we need them. So first, let's just set up the double sum that estimates the volume under the graph of this function, f of x and y equals x plus y, over the rectangle 0, 1, cross 1, 3. So our sum is first delta x, delta y out in front of the double sum because we use these evenly sized subrectangles. So that was 2 over n squared times the double sum I equals 1 through n, j equals 1 through n, of f of xi star yj star, which we just identified as f of I over n, 1 plus 2j over n. So again, that term out front is delta A, and then what we're adding up is actually just the heights. Okay, 2 over n squared stays out front, so it's going to be 2 over n squared times the double sum of, and now let's plug these coordinates into the function. The function was f of x and y equals x plus y. So it's I over n plus 1 plus 2j over n. We can split this sum up into 3 individual sums. So leaving the 2 over n squared out front, we're going to have the double sum of I over n plus the double sum of 1 plus the double sum of 2j over n. For a given partition of our domain, n is a fixed number. It doesn't depend on I and j. So we can pull some constants out front for the first and third terms. Okay, so I factored those out front. Now we're ready to look at the facts that I put at the top. The first one is the consecutive integers formula. So this is saying from I equals 1 through n, add up I. In other words, it gives us 1 plus 2 plus 3 until we reach n. This is a pretty famous formula, and it's going to be n times n plus 1 divided by 2. The next one I put up here because a lot of people mistake this. If you sum up 1 or any constant from I equals 1 through n, it's not just 1. Sometimes people think, oh, I'm not summing anything up. You're adding up 1 n times. So this is 1 plus 1 plus 1 until you've done it n times. So for 2b, I first sum up 1 n times. That leaves me with the sum from I equals 1 through n of the quantity n. But now n is just a number. It doesn't depend on I. We can bring it out in front of the sum. Again, we're adding up 1 n times, so we get n squared. N times n. Okay, so coming to where we left off the calculation, we have 2 over n squared out front times 1 over n. Now I need to add up I n times. So kind of similar to 2a, I would think of this first sum that we're going to do as I plus I plus I plus itself until I've done that n times. So that's going to be n times I. The middle term we just did in 2b, so let's go ahead and finish that double sum. It's n squared. And then adding up j from j equals 1 through n is the consecutive integers formula that we have in number 1 at the top. So that's going to be n times n plus 1 divided by 2. We can do some simplification, so I can cancel out 1 over n and n for the first term. And likewise, 2 over n, I can cancel out the denominator with the n in the numerator for the third term. I can also cancel out the 2's. Okay, let me give myself more room. Okay, so there's where we left it. We don't have any double sums left. We have 2 single sums. The first one is the consecutive integers formula now for I. So we can say that this sum is going to be 2 over n squared times the first quantity is going to be n times n plus 1 divided by 2. Then we have n squared as it is. And then in the third quantity, we need to add up the number n plus 1 n times. So that's going to be n times n plus 1. Okay, we're done with our summing. Let me go ahead and cancel out an n from the denominator in that leading term and all the numerators inside the brackets. Now let me distribute the remaining 2 over n. So the first term is going to be n plus 1 divided by n plus 2, and then plus 2 times n plus 1 divided by n. Or in other words, that's going to be 3 times n plus 1 divided by n plus 2. Given a choice of n, defining one particular way to partition the domain, this would be an approximation of the volume enclosed between the xy plane and the graph of the function. To get the true volume, we're going to see if the limit exists as n goes to infinity. So we take the limit of this expression as n goes to infinity. The first term goes to 3, the second term is 2, so overall we get 5. So the limit does exist, and we say this is the double integral of x plus y over our rectangular domain. Okay, so that's our one example of using a Riemann sum to compute an integral. Going forwards, we're going to have faster ways, so you can probably expect that in practice we don't usually do this. At the end of the example that we just worked through, I wondered out loud if the limit actually existed. In other words, can we associate to the double integral a volume under the graph of that function? In fact, there's a theorem that tells us that whenever our function is continuous on a rectangular domain, like the function over the domain that we just looked at, then the double integral does exist. So you don't have to worry that the limit of your double sum won't exist. I want to mention that this is a sufficient but not necessary condition, meaning if you're wondering if f is integrable, it is sufficient to know that f is continuous. Continuous implies integrable, but they are not synonyms. It is possible for a function to be integrable but not continuous. So often the functions that we look at are continuous, so you might have forgotten that this can happen. Let me just sketch a picture in R. So suppose I want to integrate this function y equals f of x over the closed bounded interval from a to b, but my function looked like this. Looking at this function, it has a jump discontinuity, but we feel it should have some area under the curve. Let me sketch the area. So since there is a defined sense of area enclosed between the x-axis and the graph of this function from a to b, this function is integrable from a to b. But overall, this theorem should be good news. If you're looking at your integrand and it's a nice continuous function, that means that the integral does exist. Thank you for your attention.